Last session we saw about what happens in virtual memory and how that virtual memory impacts various data structures, access, uh, how the different data structures access pattern impacts performance. So today's session will be focusing mainly on application level memory management, essentially how C++, malloc free, operator new delete behave, and then we extend that for the need of the garbage collection, how what kind of problems garbage collection solves, and how to take advantage of garbage collection essentially. So with that in mind, let's start. So before that, I want to take us cover a small part on the virtual memory, and then we'll go into the next step. Okay, let's assume that this is our physical RAM, and then we have virtual address space from multiple processes. This is my process 1, and this is my process 2, and this is my physical RAM. Okay. So typically, operating system reserves some amount of virtual memory. This is virtual memory of process 2, and this is virtual memory of process 1. Okay. So typically, operating system reserves part of virtual memory to its own use. Now, you remember libc or the operating system kernel instructions are available to all processes. Okay. And these operating system part is not duplicated in virtual memory. So in physical memory, you will find that there is a, for example, on Windows, you have NT kernel DLL. Okay. So what OS does is same NT kernel DLL physical memory address is mapped to virtual memory addresses of multiple processes. Since this is a shared area for particular processes, this memory is kind of read-only. You cannot write to this. If you try to write to this memory, it will give you an error of access violation. Okay. So the idea is that if you are writing operating system level, or if operating system is mapping part of its own memory into each individual process virtual memory, then any change in that memory will impact essentially all running memory processes or all running applications. So if one application changes that part, if application is allowed to change it, and if one application changes that memory, then it will change for every other process. And this will allow one process to indirectly access memory of another process. That is why operating system shared memory part is always read-only. So in general, in a 32-bit address space on Windows, you get 4 GB of virtual memory. Out of that, 2 GB is reserved for operating system and 1 GB is available for the OS. When you go to 64 GB RAM or 64-bit operating systems, because there is a large address space available, Windows uses a different scheme for reserving the operating system memory and the application level memory. Now let's go to actual what happens in a application memory. Now at this point, we are going to look at what happens inside a single application process and application process virtual memory address space, rather than trying to look at what happens across multiple applications. Okay, so let me go and back to again, we have a one big virtual memory address space of 4 GB, and we have a just and we have a smaller address space, of physical RAM, where the virtual memory maps the virtual address to actual physical address, and whatever is not possible to fit into the physical address is mapped into a backing store that is on disk. Let's say a new so this is your process, and that has 4 GB of RAM. Okay, I'm taking the example of a 32 GB address space, but practically the same thing will happen on uh, practically the same thing will happen for 64-bit address space as well. So a new process is started, the OS address space is mapped with NT kernel and all the SOs and the memory is loaded, and the application memory is now entirely free. Okay? Nothing is mapped yet. Okay. So now the application makes a malloc call. Maybe it is allocating just 100 bytes. The moment it does a malloc call, this is the first time internally application makes a call to the operating system saying that I need 100 bytes, map those 100 bytes to from virtual address space to physical address space. So in this case, the OS maps a virtual address space page which is about 1 KB, and then gives that one virtual address page to the process, saying that now this page is mapped to a physical memory or a disk memory. The moment this happens, OS takes 100 bytes out of it. Application takes 100 bytes out of it. How do I say application? No, malloc is not really application. It is running inside the application, but the malloc logic takes that one virtual page, extracts 100 bytes out of it, and returns those 100 bytes to the caller, whoever called malloc. He gets the 100 bytes of memory allocation. What happens to the remaining chunk in the virtual page? We'll come to that slightly later. The application then calls maybe malloc another time. This time it asks for maybe 100 KB. Though automatically the malloc then again goes to virtual memory, asks for more memory pages to be mapped, and it extends the allocated portion bigger. So far, so good. What happens when you call free? Does that mean the virtual memory pages are not mapped anymore? Not exactly true. What malloc does, or what free does, is it maintains a linked list. Now, this is a very naive implementation of free list. So I'm giving you a logical thing what happens. Actual implementation in OS is obviously slightly more complicated and more optimized for performance. So what free does, it maintains a list of free memory locations. So the moment I return a pointer to the free memory location, process adds it into its own free list. So there is a free linked list. So I have a node 1. Next time I call free, another one is appended here. Next time I call free, another one is appended here. So I did a malloc, then I did a free, then I did a free again. So in all these scenarios, the free list keeps on growing. Now, the process has an option that when a next malloc happens, it can either go to OS and say map more virtual memory, or it can go to its own free list and see if there is any sufficient chunk available in the free list and extract memory from that. Remember, so the free list may look like this. There is a first memory of say 100 bytes, then that points to the next one, which is of maybe 100 kilobytes, then maybe 100 kilobytes, then maybe another one which is 500 bytes, like this. Okay, so now if I application asks for 200 bytes of RAM, okay, it will go and check the nearest one, saying that yes, this is, I have a 500 byte chunk and I can return 200 bytes from this 500 byte chunk. Okay, so the next malloc call actually splits this 500 bytes into two portions. It extracts the first 200 bytes and returns it to the application again, and remaining 300 bytes remain into the free list. Again, remember, this is, treat this as kind of a logical algorithm. At OS level, things are way more optimized. There are multiple linked lists. There is a small memory allocation linked list. There is a large memory allocation linked list. You can do a levels of malloc where you can allocate a big chunk at the first time and then extract smaller memory locations from that chunk. There are various ways to optimize memory allocation. But remember, there is this free list is a one free list for the entire application. So if there are multiple threads in that application, then anytime the memory allocation happens or anytime free happens, because the memory allocation list and free list are common data structures across the application stops. All threads stop their work till the memory allocation completes. So threads use a lock when they are allocating memory or when they are freeing memory. So more memory allocations free you do, more can be a performance impact on you because of the locking mechanisms. Okay. Now, considering this scenario of malloc and free, are there any questions? Abhinav, what is the memory reservation model for Linux in case of 32-bit system? I believe Linux also uses something similar where there is a predefined set of memory allocated for mapping the OS, libc, and all the common DLL calls. But I'm not 100% sure if it is exactly same as Windows. Like the way Windows reserves first 2 GB virtual memory for OS use, does Linux does 2 GB? I don't know. I'll have to find out. But what is Does the 2 GB application memory include stack memory? Yes. So let me show you the redraw the page again. So this is my application virtual memory. First 2 GB is reserved for OS. This 2 GB contains heap plus stack. Okay. So the typically heap is allocated from the top and the stack grows from the bottom. Okay. So now let's look at what kind of things may happen considering the malloc and free model that I explained. Okay. So let's consider the scenario, and this is where things become complicated, and this is where you will find the need about the memory manager. Consider the scenario where I have let's take a simplest case. I have a char pointer which is pointing to a memory location. Let's say this memory location is OX 5000. Typically, it will never be 5000 because 5000 will go in the OS reserved area. So just for explanation, I'm using 5000. And this is pointer 1. And let's say I have another pointer variable which is also pointing to the same memory location. Okay, both pointers have the same value. Now the confusion occurs that who is supposed to delete this chunk of memory starting at 5000, and maybe I have, let's say 5000 or 2500, 25,000 bytes, okay, 25k bytes. So I have allocated 25k bytes and I have two variables which are pointing to that same memory location. So now all kinds of interesting things can happen. Okay, let's say I freed pointer 1. The moment I free it, remember C++ has no idea how many pointer variables are pointing to a particular memory location. So the moment you call free, this pointer goes and sits into the free list. Okay, let's say this is my free list and OX 5000 address is now sitting in the free list. Okay. Because pointer 2 is pointing to the same memory location and maybe in another class or another function. So that function has no idea that the memory is freed. Okay. So somebody does a free, then the next malloc happens, and this malloc finds that, yeah, I can reuse this portion of 25,000 bytes. So next malloc call will extract something from this chunk and return it to some other pointer. So pointer 3 is now also pointing to this allocated list. And this pointer 3 may overwrite memory. Okay, so it may write something at OX 5000. Now the next function call happens and the pointer 2 tries to access the same 5000 memory at OX 5000. Can you imagine what kind of mess it will occur? Both pointer 1 are pointing to the same memory. Pointer 1 was freed, so OS treats it as free. Then OS allocates that memory to some other pointer. Pointer 2 thinks that it still has all the memory and it continues using it. Now essentially it is using a corrupted memory pointer. Whatever information originally was stored in pointer 2 or originally was stored in OX 5000 memory address is no longer valid. This is just one case. Let's go to next one. So I'm going back to the same scenario where there is a char star pointer 1 and there is a char star pointer 2, both pointing to the same memory location and which is of 25K in size. Now look at the scenario where pointer 1 is again pointing to the same memory location and pointer 2 is pointing to the same memory location. Hello guys, I'm sorry I got bounced off. So give me a minute to share the presentation again. Okay. Uh, can you tell me, somebody can just put a chat message to see you heard up to what point? And also at any point, if you stop hearing me, just put a message on the chat. Can one of you put a message on uh, till what you were able to listen to me? Okay, so let me start on this page again. Okay. So there are two pointers, both pointing to memory location at OX 5000. And this memory location has 25K memory allocated. Let's assume that I do a call free on the pointer 1 and that adds the same address of 5000 into the free list. Without realizing that the memory is freed, the, the programmer somehow in second function calls free onto the pointer 2 as well. So the same OX 5000 address is now added twice into the free list. Can you imagine the implications of having the same pointer twice in the free list? Next malloc happens by mistake. the malloc will allocate same pointer twice. Malloc will return the same pointer twice. Now you are guaranteed in a scenario where you know or where you have no idea what kind of memory corruption may occur. Where you have no idea what kind of memory corruption may occur. That clear? Any questions so far? Guys, since yeah. Ramakant, by this model, please also explain why we have a problem with double delete even if there are two subsequent deletes for the same replication without any related allocation yet. Good question. Remember, the free list has to be efficient in terms of performance, and because we are writing memory allocator, right? So if memory allocator starts allocating memory for its own purpose, you are going to go in a for loop. Okay? You are going to go in a kind of loop, right? So you are in a situation where catch 22, egg first, yeah, hen first. Okay. So the memory allocator itself cannot allocate more memory, and since it is a performance sensitive part, it has to be high performance. So that is why when you delete the free same pointer twice, OS does not really check and goes into the free list to see if the pointer already exists. Remember, it's usually a linked list. So if it has to find out if the pointer already exists in that linked list, then it has to traverse the whole linked list again every time. Okay? That is where the performance impact happens. And this error is not detected at runtime. Uh, the problem is it is not detected at compile time, and sometimes it gets detected at runtime. Okay. So there are memory checkers which actually trace a free. Every time you call a free, it goes and checks if the pointer already freed or not. And obviously they are doing extra work in free. That is why whenever you enable these memory checkers, the application becomes very slow. So typically these memory checkers are disabled even in debug version. They are enabled only for tracing memory leaks or for debugging a specific memory corruption or memory leak. Compiler can give warning in certain scenarios that you are doing a double deletion, and then you have to really take that warning seriously. Because generally when compiler gives you warning about double deletion, it's like accurate 90% of the time in my experience. So the moment compiler gives you warning about potential memory potential memory corruption, please take it very, very seriously. So double deletion is one problem. We saw question where you delete a pointer which is already deleted. If it is accessed again and used, it gives you garbage. Double deletion can cause multiple problems downstream. What if we don't free at all? Okay. Okay, so allocate the memory, don't free it. We have 2 GB of RAM. In case of 64 MB machines, you have maybe unlimited amount of RAM as far as practically concerned. But remember, every time you allocate memory, it has to be matched in a physical address and in a disk address. So if you don't free it, more and more memory gets mapped to physical and disk address, and that drastically reduces your application's performance. So you have to decide at what point I have to free the memory. Okay. So there are multiple issues. There's one other issue that you will find, and this time I have to take you to a little bit into the C++. Let's assume that I have class A, and it contains a pointer PA. I'll call it MPA just to say that it's a member variable. It's a char star. And then I have class B, and it also has a char star MPB. Okay. Now assume that the same scenario. Okay, so both these pointers are pointing to the same memory variable. Okay. Consider the scenario that I have some function f1. It has a object A, it has a object B. In constructor, somehow the memory is allocated, and somehow I have created a scenario where MPA equal to MPB. Abhin, I'll come to your question in a little bit later. So let me draw a scenario again. Okay, so I have a function f1. I have created A, which in the constructor, let's assume I'm allocating the okay, try. Hello, am I audible now? Can you someone put a message? Let me go back to scenario again, where I have a class A, and inside that I have a member variable char star MPA, and I have class B, and inside that I have member variable MPB. Then inside some function A2, function 2, I have created an instance of A, I've created an instance of B. In the constructor, they have allocated memory for MPA and MPB. And somehow I ended up creating a scenario where I have assigned MPA to MPB. Okay, so I have two different class instances, but their member variables are pointing to the same memory location. Now, when MPA, now when the A and B object go out of scope, they will delete the pointers, right? So this is a typical scenario where a double deletion will occur. Now, if I want to eliminate the double deletion, what do I do? If I want to eliminate the double deletion, what do I do? The only way I can eliminate the double deletion is at design level, I have to decide who owns this pointer. I can say that only A can delete this pointer and B should just set it to null in the destructor. It should not delete it. Okay. So this is a design time decision that a C++ designer has to take. But sometimes it is not possible. Sometimes you are not sure A will live longer or B will live longer. And in which case, if A lives longer and B deletes the pointer, you have a problem. If B lives longer and A deletes the pointer, you have a problem. So then Hello. Hello. Guys, can you hear me? Okay, good. So let me start again. Okay, so far we have seen the scenario where we are using a low level memory functions, malloc and free, and that can cause memory problems like double deletions, which are again detected at runtime, not at compile time. And sometimes they are not even detected at runtime. Remember, even if double deletion occurs, you may discover it accidentally, or you may discover it after, say, a memory corruption happens in function X, then you may discover it after 20 other function calls. And then it will be very difficult to go back and see exactly where memory corruption has occurred. So one memory corruption is one of the nastiest bug that can happen in C++. And it is also one of the nastiest bugs where malwares and virus writers that take advantage of this scenario and they corrupt memory in such a way that they gain the control. It's very difficult, but it is possible. So far, we looked at only malloc and free. So now let's go a little bit in what happens in operator new and operator delete, and what is the difference between malloc and free with respect to operator new and operator delete. Okay. Now remember this scenario of double deletion, or where a C++ class has to decide who owns the memory. If you have two classes and if they have a shared pointer, then they have to remember who deletes the memory. So one way C++11 and C++14 address this issue is they have introduced a template called shared pointer and auto pointer, and we'll see how that benefits us after we complete the operator new and operator delete. I hope I'm audible. If not, again post a message. So what happens in operator new? And delete. Okay. So let's take a simple example of what happens when I allocate a character array. Star pointer equal to new char 100. So any basic data type when you allocate, like char, int, float, double, it essentially becomes malloc size of char into 100. So it allocates, it will take size of int 4 bytes into 100 and it will allocate 400 bytes. So this is what happens when you allocate basic data type. And this difference is important on how you use delete. Okay. What happens if I have a class? Let's say I have a class A and that has one int and one char. What happens when I do a here? Sukumar, can you hear me? Guys, can you hear me and see the presentation? Okay. Okay, got it, got it. Okay, so let's say when I say pointer to A and I declare new A, the scenario now is slightly different than a simple malloc. Now when I do new, first it does a malloc or equivalent of malloc and allocates size of A amount of memory. Now it uses this PA as this pointer and calls the constructor of A. Okay. So that is why when you get a this pointer inside constructor, none of the memory is really initialized. You have to initialize all variables that you define in a class. If you don't, then there is a chance that you will get a garbage. Now, typically, the new C++ compilers will give you a warning that if you have defined multiple constructors, it will tell you in this constructor, this variable is not initialized, kind of. Okay. But remember, now when you do a new, two operations are happening. First is a malloc, and then a call to the constructor. What happens when I allocate an array of A's? Okay. So let's say A star PA equal to new A10. What happens now? Again, first you allocate the memory. So it goes something like this. Malloc size of A into 10. Okay. Then it essentially does a logical for loop, and for each A in this 10, the constructor call happens. So when you do a array allocation, the memory allocation happens once and in a contiguous chunk, but the constructor calls will happen multiple times. So if I do allocate a array of 10, then the memory allocation will happen once. The sufficient memory to hold all 10 objects is allocated, and then it calls constructor 10 times. This has a lot of implication on what happens in delete. Okay, and what happens in a array delete and a simple delete. So far so good. Any questions on this, on new and delete? If there are any questions, please ask, because I find that in a typical C++ programmer, new, array new, delete and array delete, there is a whole lot of confusion. What happens if the constructor call fails and 4 elements got constructed? Usually, ideally, this is a messy scenario, and that is why there is a mandate that constructor cannot throw an exception. If you constructor throws an exception, then remaining objects are not constructed, but memory is still allocated, right? So what do? If you call delete, memory will get freed. Now, when we come to the delete part, we'll see how that becomes a mess. So give me a minute, Mangesh. Now let's look at what happens in a delete. Okay. So I have a first scenario, A star PA equal to new single object allocation. On this, I call a delete. It has to go exactly reverse of constructor. So first, the destructor call happens, and after destructor is done, then it frees the memory. That's what logically happens. What happens when you do okay, A star PA equal to 10, and now I call delete PA. Okay. Remember, I have allocated an array, and I have done a delete, simple delete, okay, not a array delete. In such scenario, what happen? Okay, in a typical scenario, as you have seen previously, first thing that happens is a destructor call, and then the memory is freed. Okay. Now when I do a array delete, first there is a for loop and multiple destructor calls happen. So if I allocated 10 objects on heap, then 10 destructor calls happen, and then a single free call happen. Entire memory is allocated, deallocated in one shot. Okay. Now consider the scenario that instead of, remember, I am doing a array delete here. Instead, I allocated an array, but I called a simple delete, delete PA. Then instead of for loop, only the first object destructor will get called, and then the entire 10 objects will be freed. Okay. It's a very tricky scenario. If my destructor is actually a do nothing destructor, then these two scenarios are don't have any big difference, because memory is still freed in both scenarios. However, suppose class A is actually has another pointer inside, then only for first object that pointer will get freed. Remaining 9 objects, because the destructor is not called but memory is freed, it will result in a weird memory leak scenario. Or in those second remaining 9 elements, you are trying to close some file pointer, those file pointers will remain open. So be very careful in using. If you allocate array, use array delete. If you allocate a single object, use a single object delete. Okay. But this does not make any difference. Array delete or normal delete does not make a difference when you are using a basic data type. Okay, so if I did a char star PA equal to new char 100, okay. Delete PA is exactly same as delete array PA for basic data types. Why? Because there is no destructor. When you call a delete on a basic data types, it just frees the memory. Okay. Because there is no destructor, there is no difference between an array delete and a single object delete. Okay. Now, Mangesh, going back to your question, okay, consider the scenario I'm doing an array delete, right? And I did a new of 10 objects, and on fifth object, 4 objects got constructed, fifth object results in a destructor. Now you have a mess on how to call a delete. And only recently, I think C++11 is where they put some condition on how to handle these scenarios. But even there are a lot of edge cases which don't get handled properly. So the sane advice is don't throw any exception from the constructor. If you are calling some function from a constructor and that function is throwing an exception, then add a try catch inside the constructor and don't rethrow that exception. Does that answer your question? Please post a Mangesh, please post a message if that answers your question. Tanvi, I did not understand. Can you please give me an example of such scenario? Can you put something on what kind of scenario? Mangesh, go ahead with your doubt. Please post. Meanwhile, Tanvi, I'm not sure if I gave you the correct scenario. Abhinav, if you have overridden operator new and that throws an exception, then your constructors will not get called at all. Because remember, operator new, if you have overridden operator new, it actually just allocates memory. It does not make the constructor call. Constructor calls are generated by the compiler. So if new throws an exception, then there is nothing like while creating fifth element memory for an array of 8. You either create the memory for the entire array size or you don't create at all. Okay, so if new throws an exception, constructor call has not happened. So you just catch the exception and say, okay, nothing happened. Because the constructor has not happened, there is nothing to clean up. I hope I have answered your question. Scott Mayer's book, he says that raise an exception from the constructor so that incomplete object creation does not happen. The problem is C++ is very fuzzy on how do you create an object. Okay. So Scott Mayer also says that don't do any real work in the constructor, just initialize variables. And if you do that, chances that the object fail are low. Ramakant, throwing, at least in my opinion and my experience, throwing an exception from constructor is not a best practice for C++. But for .NET and Java, yes, throw an exception from the constructor. And why that is allowed is because .NET and C# use garbage collection and not the manual memory allocation and initialization. The other difference in C# and .NET Java is when you allocate a memory, the garbage collection sets that memory to non-value like 0. C++ doesn't do that. So my advice is still don't throw exceptions from constructor. Okay, so I think our 1 hour is over. If you have any questions so far on what we discussed, please post a message. I honestly did not expect memory management to take so much time. We have not yet touched the garbage collection yet. So I think we need a memory management part 3 where we will go into first a concept. Mangesh, I'm going to cover shared pointer in detail in the next session. So if you have a question on shared pointer, it will be good if we discuss it on the next session. So in next session, I plan to cover on the first concept called RAIC, or resource acquisition is construction. and one of the resource is memory, but you can use the same strategy for things like files and database connections, cursors, to appropriately close the file or cursor at the correct point. The auto pointer or unique pointer is an example of resource acquisition or its construction idiom. So will you see how to use that and where are the scenarios where it fails? Memory pool concept, yes, I plan to take it in next session. There is a concept of allocator, which is essentially the memory pool concept. And memory pool is also used in garbage collection. So Abhinav will cover memory pool also in the next session. So next session I plan to cover RAIC. Is it possible to decide page size from application? No, there is. If you're talking about virtual memory page size, then this is a OS level testing. There are ways to change the page size at OS level, but then it impacts all applications. So individual application cannot change the virtual page size. But I think I've answered your question. So going back to the next time session, we are going to first talk about RAIC and what are the problems it solves and what are the problem it doesn't solve. Then we'll go into reference counting for memory management, which is where the shared pointer comes into picture. And that is one of the strategy for garbage collection. And then we'll go to generational garbage collections, which is typically what is used in Java at low level in Java and C Sharp. Again, we are going to talk more about the concept of generational garbage collection and the concept of mark and sweep memory tracking and freeing. Uh, and then we'll do some touch a little bit upon what different languages use, like what Python uses. For example, Python uses a combination of reference counting and generational garbage collection. Java typically uses generational garbage collection but does not use ref counting. So there are various languages which use design the garbage collection in different ways. And remember, garbage collection strategy has a large impact on applications performance. Same way, memory allocation and free strategy has a large impact on application performance. So at the end, I just want to give you a small anecdote about how the memory allocation can impact performance. Uh, Initially, Linux and Windows both had problems when you allocated a small memory, like less than 20 bytes, a lot. Suppose you allocated 20 bytes for 100,000 times, then those kind of memory allocations were actually had a big performance penalty. Your application becomes slow.